All right, so welcome everybody to one more public guest talk at Montréal MLOpt. So for our seminar series today, we have a very special guest speaker, Dr. Ashia Wilson, who will be starting at MIT as an assistant professor in January, if I'm not making a mistake. And up to now, she's been at Microsoft Research as a researcher. And before that, she got her PhD at UC Berkeley. She has a very exciting line of work for many of us, this variational approach to a number of interesting topics related to machine learning, algorithmic and inference, and fairness, which is an interesting connection to draw. So Ashia, I will stop here. Welcome. And the floor is yours.
Great, thank you for that wonderful introduction. I probably should have updated this title page because I am in between my postdoc at Microsoft and starting in January, as you mentioned, at MIT, so taking a little bit of a break. But yeah, this is a talk that'll be about work I've done probably for the past 2 years and into my postdoc. The first part will be discussing, which I think overlaps with some material I've presented here before, but the other two topics, inference and fairness, represent my most recent work. So I'll also discuss kind of what I've been thinking about as related to these two topics. Good, great. So basically the paradigm that I'll be presenting is thinking about machine learning as a prediction-aided set of decisions. And a very naive kind of pipeline for machine learning is the following: just formulating any kind of problem you have as a prediction-aided set of decisions, collecting a data set, forming a predictive model from that data set, and then using it to aid in decision making. So as a specific example, perhaps one person, you would like to decide who to hire. A machine learning person might think, okay, let me collect a data set, form a predictive model from that data set, and then use that to just make my decisions, my hiring decisions. And so I want to highlight three kind of key components to this pipeline. Algorithms are a huge part of generating our predictive models. I'd argue that they actually constitute a huge part of this entire pipeline, but I'm going to highlight the predictive model aspect. And inference, of course, going from finite data to a predictive model that's meant to represent kind of the full landscape of data one could have seen involves inference, and that's a key component, trying to quantify errors and have that aid in our decision making. And last but not least, the context surrounding how do you formulate any given problem as a prediction-aided set of decisions, and how ought those predictions be used in the decision making. I think this is where fairness and a lot of other kind of more socio-technical influences on machine learning come to bear. And so I've been thinking a little bit about this wrapper as well. So the outline of this talk will be as follows. I'm going to present some of kind of my older work on variational perspectives on gradient-based algorithms. So this is kind of a lot of my work has focused on accelerated gradient methods and dynamical systems perspectives. And so I'll just kind of highlight that and point to where I've been going. Then I'll talk a little bit about my more recent work having to do with inference. So recently I've been working with some fellows at Microsoft Research, Lester Mackey in particular, and Max Casey at Harvard. And we've been thinking about how to speed up cross-validation, which is a technique to provide kind of sense of a generalization error for your predictive model. And last but not least, I've been talking to some scholars about fairness, in particular, thinking through how feedback loops can occur using machine learning algorithms and how to quantify these loops and mitigate against them. Okay, so those will be the three parts of my talk. And I'll start with this algorithms component. In particular, I'll be touching upon three papers that I've had. I think I've presented most of these papers here before, so but I'll give you a very broad rundown of the perspective, at least that I have, of these general topics. Okay, so the part that we're thinking through is algorithms, and as I mentioned, this is more the predictive model this is the tool through which we develop a predictive model, typically by minimizing some sort of empirical risk over a data set. And so recent years have seen significant progress in gradient-based optimization, which is the key tool for generating predictive models. And I think a lot of research has been funneled through this question of how do we develop fast algorithms for any given problem. Right now, the field has shifted a lot to thinking through stochastic algorithms and deep learning. And so I've tried to gravitate a little bit in that direction, but even kind of basic question is still kind of a curiosity that at least I had when I began this line of work. So this talk will be discussing variational perspectives on developing fast gradient-based methods. In particular, I'll be thinking through, can dynamical systems provide insights to developing fast algorithms, and what role there is to play for kind of a more numerical analytic form of thought in this regime. So as I mentioned, this dynamical perspective really pervades a lot of my work, thinking as discrete algorithms, so mappings that take discrete steps, as discretization of ODEs or SDEs, PDEs, so dynamical systems, functions of a continuous time. And so one of the kind of key ways this plays out is thinking about acceleration in particular. This is a really big starting point for my work. So very classically, gradient descent, or even stochastic gradient descent, has an interpretation as a dynamical system. So gradient descent here, I've represented epsilon as the step size, has some very classical results. One of them being that if your function is convex and your step size epsilon is small enough, then gradient descent will find the minimum of your convex and smooth function at a rate of 1 on k. So this is very classic non-asymptotic result, and it very much runs parallel to this dynamical systems perspective, where it can be viewed as discretizing this first order ODE called the gradient flow equation, which also has a nice Lyapunov analysis that accompanies it and obtains a very similar convergence rate. So the structure of these two, the algorithm of the dynamical system flows very nicely and has this structure whereby even the analysis has very deep connections. And so a very big starting point for our work is thinking about accelerated gradient descent, which adds an interpolated step to our gradient descent step, and in doing so, obtains a faster convergence rate for the same complexity class. So namely, if your function is convex and smooth, and again, your step size is small enough, then you obtain an upper bound, a convergence rate upper bound on the order of 1 on k squared. And a starting point for our work, and I think a perspective that got lost a little bit when this algorithm was first developed, is thinking about accelerated gradient descent as a momentum method, in particular as a discretization of a second order ODE, second order in time, that is. So work that crystallized this point of view was a work by Sue Boyd and Candes in 2014, which showed that the continuous time limit, or one can take the continuous time limit in a certain way and derive this ODE. Of course, there have been a lot of works that have actually followed this up, and there are many ways of taking continuous time limits. So there are high resolution ODEs and other ways of thinking through what dynamical system best models accelerated gradient descent. The reason why I think that this work is particularly nice is because they also show that the analysis follows this nice parallel structure, whereby we can present a Lyapunov function in continuous time, and this is runs very much parallel to the Lyapunov function through which we verify convergence rates in discrete time. So that's just kind of the basic template. And so, upon seeing this result, a couple of thoughts arise. First, there are many descent methods. And by that, I mean, there are many algorithms that, generally speaking, approximate the steepest descent dynamical systems on some space with respect to some objective function and some metric. And so there's a question, a fundamental question of how far the acceleration concept extends. Can all these descent dynamics have a momentum added to them and be discretized to improve performance? So here's an example of, or some examples of the descent dynamics I'm talking about, or algorithms that have this interpretation. So a lot of them are Euclidean, or like more Euclidean-based algorithms, but actually a number of them are used for sampling and in more kind of structured regimes such as learning. So there's a question of, can we accelerate sampling, for example? And can we extend this beyond kind of this naive Euclidean structure? That's kind of where my work has been heading. And so to really answer this question, it's been kind of we thought a really good starting point would be to understand the acceleration concept a little more intimately. So we had a series of questions. First, as I mentioned, what is the scope and what are the general underlying principles through which we can obtain cell acceleration, and does it apply to all these? What kind of techniques use second order ODEs that might be said to model accelerated dynamics? So I think the Nesterov algorithm I showed you on the previous slide is a basic Euler discretization, but there are other numerical and analytic techniques with other advantages you might want to consider. And so there's a question of, can we show that these might have practical advantages in the context of optimization? And finally, the first question we considered, and the question I'm definitely going to start with, is what characterizes these second order ODEs, and are they optimal in some way? And so this may have, some of you may have seen this work, but I'm just going to review kind of the perspective we developed in thinking about acceleration from this variational perspective. So when thinking variationally about dynamical systems, it's very natural to turn to physics. So in a basic mechanics course, an example might be given of a girl throwing a ball. And I think one of like the first classes you might learn this kind of very important Newton's law, F equals ma. But I guess so F equals ma here, the acceleration is given by the second derivative. The force here is represented by the gradient of this potential F, and the mass I've set equal to 1. But another way of representing Newton's law is this principle of least action. So what it does is it considers all the paths starting from this beginning point to the end point, and characterizes the trajectory that the ball ends up taking as optimal with respect to this action functional here, this minimization of this, the integral of this Lagrangian. So if you take the functional derivative of this least action problem, you obtain what's called the Euler-Lagrange equation, given here. And so we can describe Newton's law via this Euler-Lagrange equation as the stationary condition for the following Lagrangian, or action given by this Lagrangian. So this Lagrangian is very classical on so you have this kinetic energy term, which is given by the 2 norm of the velocity, and then you have a potential energy term, which is given by the potential F. And so one nice thing, there are a lot of nice things to learn about this Lagrangian formulation, namely energy is conserved, so the barring hit the ground, the ball will move in kind of continuous motion on the level sets of this, well, it's Hamiltonian, which is this Fenchel dual. But we use this kind of interpretation of this characterization to also think through what the dynamical system given by accelerated gradient descent, what kind of action it would be minimizing. And so we came with this damped Lagrangian. So you think about it as this classical Newton type Lagrangian, but damped by this T cubed term. And so what we did is we took a lot of the accelerated algorithms and took their continuous time limit and came up with a little bit more of a general object, which we refer to as this Bregman Lagrangian. So this generalizes the Lagrangian I showed you in the previous slide in two ways. The first is that we have this general term P, which represents the speed at which this dynamical system is traveling along the same curve. And then we also have generalized this kinetic energy term. So before we had the 2 norm of this velocity term, and we've replaced it by what's called a Bregman divergence. So it's the error in our first order Taylor approximation of a function h. And what we're able to show is that if h is twice differentiable and we actually need it to be strictly convex, then the Euler-Lagrange equation can be computed as the following second order ODE. And furthermore, we can exhibit a Lyapunov function given here, which shows a convergence rate of this Euler-Lagrange equation to the minimum of f when f is convex at a rate given by t to the p. So this Lyapunov function is positive and decreasing along the trajectory of the dynamical system. So that's kind of a motivating structure for thinking through perhaps how to provide a general template and perhaps map the acceleration phenomenon to different spaces. That is part of the advantage of going to this Lagrangian perspective. And so part of the contributions we had with regard to this line of work was kind of giving more of a general analysis of acceleration for convex optimization. Particularly, we show that you can take any algorithm that satisfies the following progress condition. So we need an algorithm which is decreasing the function value at a rate that can be characterized by the norm of the gradient to some power, and that power is given by p. It's kind of a nice power here. And so if you can show that any kind of algorithm has this descent condition, you can already generate a convergence rate via standard Lyapunov analysis. And all you need is that the function is convex. So this is, but you can also show, even without convexity, it will find stationary points quickly at a rate characterized by p. And for strongly convex functions, you can show that it'll find a convergence to your minimizer linearly. And in fact, you don't even need strong convexity. You just need what's called the PL inequality, Polyak, and I cannot pronounce the last name well, so I'll leave it there. But you just need kind of a nice quadratic lower bound to your function. So there's this nice template, but if you just simply couple this descent algorithm with a discretization of that Euler-Lagrange equation, you can systematically speed up the convergence rate of that algorithm. And so yes.
We have a quick question here from our text, from our chat. Reza is asking about the meaning of delta and this kind of assumption.
So delta is some constant greater than 0. Importantly, it doesn't depend on the state. And so the reason is it constitutes, at least here, a discretization parameter. So another way of thinking about this is you need some sort of, the time derivative of your function needs to be decreasing. And similarly, you can show a similar kind of set of complexity bounds. And here we have this delta representing the extent to which you can discretize, and that'll probably play a role in the step size you choose for the algorithm.
And I guess I have a follow-up on this. So at this point, you're making this assumption and you're getting these bounds, and it's a separate step, and it's a whole nother proposition that would say for this class of functions, then delta is this much, for example.
Yeah, so essentially what you're doing is you're characterizing a family of algorithms as algorithms which can satisfy this descent condition for some delta and p. And then what I'm trying to say is that this is the set of algorithms that can be naturally accelerated via this specific discretization of the Euler-Lagrange equation. And so, for example, mirror descent or natural gradient descent, there are several other algorithms that you can show under certain conditions on your function class, and for different choices of delta and p, this condition will be satisfied, and it's exactly for that complexity class. You can kind of wrap it or in this Euler-Lagrange discretization and obtain systematically faster convergence rates, so accelerate mirror descent or natural gradient descent.
So then Reza's follow-up question on the chat that I see here is whether we can always make this happen using line search or some of the, I guess, the standard gradient descent-like methods. Reza, if I made a misinterpretation of your question, please feel free to unmute yourself.
Is that the correct interpretation?
Yes, he's happy with it.
Okay. There are a lot of algorithms through which you can make this descent condition happen via a line search step, but I'm not quite sure the extent to which line search will, you can plug that into any kind of algorithm and eventually you'll satisfy such a progress condition. I think in principle, we call these like descent conditions because you do need to be able to have your function value be decreasing at every iteration, and only certain kind of algorithms do that. And then I'm pretty sure if you add a line search step, then you can kind of tailor this progress condition appropriately. But yeah, that's actually something we were thinking about. And in fact, we actually characterize another acceleration which adds a line search step and actually obtains systematically faster convergence rates. So this was kind of developed by Montero and Spector, I think. And what they showed is essentially that for higher order like tensor methods, so essentially like cubic regularized Newton's method and a couple other, if you take higher order Taylor expansions of your function and regularize them for this family of tensor methods, if you add a line search step, in addition to essentially doing this coupling with this Euler-Lagrange discretization, you can get an even faster convergence rate in the case that p equals 2. So when p equals 2, these two cases match, and there is of course a lower bound. But the lower bounds for that other complexity class actually match this rate. So this is known to be optimal for tensor methods, for regularized tensor methods.
Okay, so I think your last sentence is related to another question by Sharan. Sharan, you're welcome to ask the question yourself if you want.
Sure. So these results, we can get it by a discrete time analysis as well, right? So the continuous time perspective helps to like strengthen something, or?
Yes, it strengthens something. So you can show that the Nesterov style and the Montero-Spector style, they have the same continuous time limit, at least if you take it in the same way. I'm sure at a high resolution, there might be some distinction between these two techniques, but at least the low resolution ODEs agree. And so the discrete time is when this is showing up. And that's where the line search step is giving you benefits.
But doesn't Nesterov have like an equivalent result for like p smooth functions, like where the pth derivative is smooth? And
yeah, that's exactly right. So Nesterov has a paper in which he obtains this first Nesterov style results. So he gets this complexity bound for these smooth tensor methods, or for these tensor methods is applied to smooth functions. Smooth meaning your higher order gradient is smooth. So like the pth order gradient, if you're taking a pth order Taylor expansion, what he shows is that you get this 1 on k to the p convergence rate. This other paper was saying you can get a systematically faster set of rates. So it was close to optimal, but it is not optimal. And these techniques, adding this line search step makes them optimal. So I think there were like 3 authors, Sebastian Bubeck and crew, and there were 2 other, Gaskanov. I think there was a series of papers which showed that this Montero-Spector style gives you the lower bounds. That was, I think, in like 2018 or so.
I see. Okay. Thanks.
Great. So essentially, what I tried to mention is that, like, because the continuous time limit of these 2 techniques are the same, it's no surprise that the analysis is very similar. You exhibit the same Lyapunov function. Essentially, you're just showing decrease in the algorithms. And so given this framework, we were just trying to understand, okay, I just need a descent method. And then once I have that, I can get faster complexity bounds just via these 2 techniques. And the hope is that for whatever function class I'm dealing with, that would render my technique my subsequent technique optimal. And so I want to demonstrate how we kind of laid this to bear. But another kind of question before I kind of get into that part is, we were really interested in new algorithms for optimization. So one work I had with some co-authors, Michael Betancourt and my advisor, Mike Jordan, was to figure out, okay, we had a Lagrangian system and subsequently a Hamiltonian system. Can we use techniques for discretization that are specific to Hamiltonian systems, and would this confer benefits in practice? And perhaps theoretically, perhaps some form of robustness might come about. And so in particular, we're thinking about symplectic integrators. So these are numerical integration techniques that are said to preserve the symmetries in your dynamical system. And so it's clear what this means for a dynamical system or a Hamiltonian system through which energy is conserved. You have this nice symplectic Sioux form, and it has oftentimes a physical interpretation of something that you can exhibit in a physical reality as being actually preserved or conserved throughout the trajectory of the dynamical system. But it's not as clear actually what this means from the perspective of the system. And so what we're hoping is that the symplectic 2 form represented some kind of notion of convergence, and that perhaps applying a symplectic integrator gave you a kind of more systematic way of thinking about why such discretization might lead you to kind of better performance. But that was actually quite hard to show. I think in a follow-up paper that my advisor had with some people at Johns Hopkins, they were able to show something to that extent, I think with strongly convex functions. But what we were able to show at the time was simply that this can yield nice theoretical improvements. So we had some examples, logistic regression, worst case examples, so quadratic functions. And what we were able to demonstrate, at least empirically, is that these symplectic integrators actually tend to perform just as well. And we provided some suggestion that they might be more robust against larger step sizes. So the plot on the right is showing that when we took both step sizes up in a way that corresponded to in a systematic way across both algorithms, that eventually the Nesterov algorithm diverged, but the symplectic integrator seemed to be continue to converge, which suggests to us that perhaps there's some robustness properties to be obtained. But we were actually not able, that was kind of something we were still hoping to follow up on, because it was still unclear whether this would give you or confer practical advantages, in which cases we could describe that this phenomenon could happen. But one other work I want to highlight, because this spurred other works that were thinking about other numerical integration techniques. So a group out of MIT, Zhang and Shra, and I think Ali Chababai and a couple others, they applied Runge-Kutta integration techniques to these dynamical systems. And what they were able to show is that this outperformed accelerated gradient descent in a couple of key examples. So in particular, they were actually also able to get theoretical convergence rates, which is something we were kind of struggling with the symplectic integrators. So they were able to prove that these methods outperform accelerated gradient descent in certain cases. So here were the 2 cases that they studied. So the first example is this LP norm to the pth power, and I think the plots I'll be showing is for p equal to 4, and the example on the right is just logistic loss. And so they plotted gradient descent, accelerated gradient descent, which of course you'd expect did better, and then this was in the green is their Runge-Kutta integrator techniques, and they were able to show that in theory for both examples, these were the cases in which you could prove faster performance. So
question?
Yes.
So about this, is it correct that they're talking about a slightly different complexity class?
Yeah, I actually was going to get into that. Yes,
Okay.
they are talking about, they're lower bounds, so you need additional structure to show you're going to outperform, at least in a theoretical sense.
Right.
And another important thing to note is that Runge-Kutta integration, if you have the way the integration works is that if you have a vector field, each step of the integration will require you evaluating the vector field at various points. So what this means in the context of accelerated gradient descent is you're going to be evaluating the gradient multiple times for a single step. So, I mean, it's just a gradient evaluation. So in principle, it shouldn't be too much more expensive, but it is a little, you're having multiple gradient evaluations depending on the order of your integrator. So I think this was like 2 or 4. I'm pretty sure it was 2. So they had 2 gradient evaluations for this plot.
I think it grows linearly, right? Or maybe you have as many as P, I guess. And we have one more question by Tim. Want to ask your question, Tim?
Sure, but I think we're basically past that point. I asked that like a while ago, so maybe
sorry.
it's not.
Oh no, I see now the time count. It has been 7 minutes. It was 7 minutes ago. I'm sorry.
I'm going to pause the section. I can do the back 2 slides. We can discuss if you want to hold the thought.
Yeah, let's shelve it for the end.
Okay. So one thing we were hoping to, I thought this work was quite interesting, excellent, because it was able to actually prove theoretically that there might be something to exhibiting dynamical systems and applying numerical integration techniques. But you know, we have this template for acceleration that I illustrated on the previous slide, and so there was a question of, you know, given this additional structure for these examples, is it possible that a simpler discretization will work? One that maybe wouldn't involve multiple gradient evaluations per every step. So what we were trying to do is we actually, by coincidence, we're also looking at this other class of dynamical systems that we exhibited in this Lagrangian paper. So what we did was we took the continuous time limit of these higher order gradient methods, and we showed that their continuous time limit was what we call this rescaled gradient dynamic. So if P equals 2 here for this first order ODE, you simply get the gradient flow. But for P greater than 2, what you're doing is you're rescaling the gradient by its norm to some power. So if P is infinity, this is what's called normalized gradient descent, and it has been studied quite a bit in the context of optimization. In fact, I think Cortez or a couple people showed that you can get finite time results for this dynamical system in certain contexts. So, but this kind of interpolates between this gradient flow and the normalized gradient flow as a function of P. And so this was an interesting class of dynamical systems in particular because you can exhibit a Lyapunov function. So first of all, you can show that it satisfies this sufficient decrease condition and subsequently show a convergence rate for convex functions. It also converges for non-convex functions, and again, for this PL inequality class of functions. So it has broad, unsurprisingly perhaps, broad guarantees that you can obtain. And so we were looking independently also at what happens if you just take a naive discretization of this dynamical system. The reason why we wanted a naive one is because we wanted a simple algorithm, something, you know, just involving gradients. And so this was this rescaled gradient descent thing. So you have normalized gradient descent again at the one end of the spectrum. And so what we were able to show, actually, surprisingly, is that this gradient descent, or this algorithm, satisfies our requisite progress condition exactly for the class of functions that Runge-Kutta was getting empirical theoretical convergence guarantees for. So it's something what was called strongly smooth functions. It's a pretty complex condition, but you have to have some kind of structure characterizing the higher order gradients and the gradient. They have to kind of behave in a similar way. but I omitted some of the details. So I have a backup slide if anyone wants to see that in particular. But I do want to kind of stick to the high level form of this work. So basically what we were able to show is that you can get this kind of progress condition for this class of functions, and subsequently you can add those two frameworks of acceleration, Nesterov and Monteiro-Sveiter, and improve its convergence. And so we did just that. We took the accelerated version and added the few lines of code to plot that, and it just pretty much systematically outperformed Runge-Kutta on these examples as well as others. So it was kind of, they also had kind of a nice parallel structure to this family of algorithms by Chris Madison called Hamiltonian descent methods, I think he named it. So they kind of look like very similar algorithms. So perhaps there's a more meaningful connection to be drawn there. But in particular for this class of functions, these algorithms seem to at least theoretically and empirically perform quite well.
Well, question by Tim, and this time I think I only lagged like a minute or two. Okay. Tim, want to ask your question?
Sure. I was just wondering that you mentioned that for the non-convex case under the KL in the property, you get similar convergence results. Are these global or local results?
They're global results, and in particular, so it works for the KL condition or the PL condition. It's not, the PL condition, but it actually works for a much broader condition. So the PL condition is essentially that your, I think, function value is related to the norm of your gradient, or the norm of your gradient to the squared power. If you just have any kind of power there, then you'll get global convergence results for this class of functions.
Okay, thanks.
So just kind of to highlight some of the contributions we've provided thus far, do you think that dynamical systems can provide kind of avenues through which you can think through how to develop algorithms for optimization? I think one of the key things I've taken away is that the Lyapunov analysis helped me to understand at least what was going on in my own way, just coming from more of maybe a dynamical systems background, how these algorithms were being developed and analyzed, and therefore perhaps how to extend them in different contexts. So for example, right now we're working or thinking through kind of the Riemannian context, and it becomes a little more easy to think through developing tools to analyze algorithms in these settings. And so, and the variational perspective is interesting. We haven't kind of revisited it since introducing it, but it'll be interesting to see if this kind of stays preserved with respect to, like, a lot of other people are introducing dynamical systems that do converge as quickly as the ones we introduce. And so there's a question of whether they also have this variational perspective and whether there's a connection between all these algorithms. So I would say that that's slightly underdeveloped. But at this point, I've kind of highlighted at least the work I've finished with respect to this algorithmic perspective. So I'd be happy to take questions before moving on, if there are any. I know there were a couple asked already.
I think we got most of the questions, with the exception of the one that I missed from Tim. So since you're moving to a completely or slightly different subject, maybe it's a good opportunity. Tim, your question about this paper by Atouche.
Yeah, I mean, it's a question / remark, because I sometimes feel like that not too many people ever mention this paper. There's a paper by Atouche and Pesquet, which basically says that the convergence rate for accelerated proximal gradient, which is just one instance of what you presented, is actually little o of 1 over k squared, and not just big O 1 over k squared. And I was just wondering, I mean, not just to you as a question, if that paper is known in the community, and if this little o could also be like squeezed out of your pretty cool unifying view.
Yeah, I was aware of that paper. I think, but I haven't looked at it in enough detail to understand if the tools used could be mapped onto some of these other settings. That said, definitely a great idea to revisit. But I do remember seeing this paper. I thought it was pretty cool. So
it is also somewhat, I think that the proof also relies into embedding the discrete case in a continuous case. And then because it's non-smooth, you don't just have like a differential equation, but it's like a differential inclusion type thing. But maybe it just complements what you did. But I was just curious if other people knew that. But anyway.
Yeah, I think the proximal methods are kind of based on more of an implicit Euler discretization, and so as you mentioned, you don't need the smoothness conditions, and so I'm wondering if what role it'll play in these higher order methods, if any. But yeah, maybe for like more of a forward-backward splitting or something like that, I could see. It's a very interesting line of open work to move into, but I haven't actually thought about it in any kind of detail. So thanks for mentioning it, though.
Thanks.
Yeah, absolutely. Okay, so I'm going to pivot a little bit and talk a little bit about a project I did with Lester Mackey and Maximilian Casey. So this is a paper looking at cross-validation and how to speed it up in certain contexts. So this is with this kind of inferential part, how you're going from data set to predictive model, and you want to understand how reliable the predictive model is. What will its out of sample performance be? So this can help be useful information, perhaps when you're making decisions based off these predictive models. And so we're going to be focusing on in particular regularized empirical risk minimization. So this is when I can decompose my objective function into a loss plus a regularization term. And two of the key problems I mentioned will be the assessment problem. So how will my predictive model perform on future data, as well as model selection. So I want to select amongst models that which will give my best out of sample performance. And in the context of regularized empirical risk minimization, I'll be specifically looking at how do you pick the regularization parameter lambda to give the best out of sample performance. And so cross-validation is, at least for more classical statistics, my background is in statistics, is one of the de facto standards for addressing these problems. And so just to kind of give you an overview of cross-validation for those of you who aren't as familiar. So regularized empirical risk minimization works as follows. As many of you know, you get data points, you form an objective, an empirical risk, which is usually the sum of the data points. And then you minimize it and you get a predictive model from this procedure. And so the way cross-validation works, in particular, I'll be talking about leave one out cross-validation, although this will extend to leave k out for k more generally, ranging from 1 to n, the number of data points. Works as follows. So you take a data point, you remove it, and that forms what's called this leave one out, or what I'll be referring to as a leave one out objective. So it's the sum over all the data points except the one I've removed. And then you minimize this. And then essentially you just repeat this procedure for every single data point. So you're performing in separate minimization problems and getting in separate predictive models. And at the end of the day, what you do is you average these predictive models. And this average is the standard way of approximating test error. So there's some nice results, classical results, showing that this is a nice Monte Carlo estimate for what you're going to be, for what is your test error, assuming, ID sampling and whatnot. And so one of the longer standing challenges is this is a really, it gives you nice guarantees, but it's obviously very, very expensive and does not scale. Like it's not used in modern day deep learning, for example. I guess leave just in mind, like we use just the test error proxy for our validation, but But this is kind of more in more small data settings, this is what's done. And so there's a question of, can we get similar guarantees without performing all these optimization steps? So the problem of finding a computationally cheap approximation for cross-validation has actually seen some recent progress. So kind of one of the leading sets or the leading set of solutions for this kind of problem is to optimize an inexpensive surrogate function for the leave one out loss. So the basic idea is, you know, if cross-validation is obtained by minimizing all these leave one out losses, perhaps I can minimize cheaper approximations to the leave one out loss, and I get these kind of approximate leave one out models. And then I can kind of quantify how close the leave one out model and its approximation will be based on how close these objective functions are. And the key tool we use to do this is very simple approximation lemma that, you know, I'm sure has appeared somewhere, but it was a handy tool. So it says essentially that if you have two objective functions that are close, and one of them has curvature near its minima, so you need some sort of quadratic curvature condition, like a PL inequality, and even more nicely, it would be nice if you had strong convexity, then their minima will be close. So basically, if I have a nice curvature for my loss function, my risk function, then I can approximate it. If my approximation is close enough, then I could just simply use that, because I know that their two minima will be close enough. So we took this lemma and tried to kind of use it to frame a lot of the recent progress on approximating cross-validation. So one of the most common tools now very popular for approximating cross-validation is essentially to use a Newton step. Worm started from the training set optimizer. This is it bears very close connection to kind of an influence function-based estimate or approximation to your model. So here, what you have is you have your empirical risk theta hat, and what you do is to obtain these kind of approximations to the leave one out loss, all you do is you add this kind of Newton-like step to each one, where the step changes based on the data point. So you have to do this, like instead of in optimization problems, you're replacing it with in Newton steps. So there are two ways of computing this Hessian. One was one was proposed by Reyhane et al. And what they looked at was this kind of leave one out Hessian. So you have to compute this in times, compute the gradient, and then kind of perform this inversion of this Newton step in times. A much less expensive approximation is to use the same Hessian for every single point. So just essentially compute the Hessian of the empirical risk. And so this has bearings to that influence function based estimate, and then just use that to approximate the leave one out models. So these are the two things that are used. And if you think about it, these are simply just optimizing Taylor expansions of the leave one out losses. So one is exactly a second order Taylor expansion, and the other one is a quadratic approximation that replaces the leave one out Hessian with this fixed Hessian. So based on this, we can just use that lemma to automatically derive guarantees in a much more precise way of how well these approximations will do under which settings. So we were able to derive this theorem that essentially just says that if you have this kind of curvature and you have Lipschitz Hessian conditions, so you need the gradients to be, or you need bounded moments, and you need some kind of smoothness that will make sure that the approximation to the objective and the objective are sufficiently close. Then you can essentially say that the cross-validation error, so this approximation to the test error, and the one that you get by using this approximation will be on the order of 1 on n squared close. So this will be within statistical levels, so it'll provide you a meaningful estimate of the test error. So that's will kind of characterizes some large-ish set of objective functions through which these approximations will perform quite well. And this kind of gives a little bit more precise characterization than what was previously known. So the Birami paper does give a similar-ish result, except for they kind of don't characterize the dependence on lambda for this constant. And they also need these statistical assumptions that we're able to do away with. And similarly, the other paper, which uses the leave one out, or rather the fixed Hessian, also kind of has a similar result under more restrictive assumptions. So we're able to get rid of this assumption that your parameter space is compact, for example. Results, we were able also to address this question of model selection, which was not addressed by these aforementioned papers. So I think one of the most standard uses of cross-validation, at least for economists in in a lot of settings, is just simply as a method through which we can perform model selection. And so we really did want to answer, when will these approximations give similar results to cross-validation for the purposes of model selection? And this was kind of recently characterized as one of the more leading or pressing questions for this line of work. So we thought, oh, maybe we'll pick this up and try and answer it. Mainly leaning on that tool. It seemed like that tool was kind of this nice, concise way of addressing a large variety of questions with regards to these approximations. And so essentially under the same assumptions, you need curvature. Bounded moments essentially means that you need the Hessian times the gradient to be bounded. And you need the addition of also bounded Hessians. You don't need them to just be Lipschitz, but also bounded. But under these settings, you will obtain models that are close, statistically close. And so far as you trust the models obtained via cross-validation, approximate cross-validation will give you close models. So that was a nice-ish result. So we were really more interested, how does this actually work in practice? And so what we did is we took a lot of the plots in the previous papers and tried to understand what are the failure modes and can we address it? Can we scale this to larger risk functions, ultimately, hopefully, bringing these tools to bear for more modern day machine learning problems. And so we were struck in particular by this plot by Tamara Broderick's group. And in particular, it shows that the test error, which is this black line, this is a simulated data set, tracks the cross-validation error somewhat well, except for, small values of lambda, you can see some kind of departure. But approximate cross-validation, at least the one that uses the leave one out Hessian, which is in green, seems to track both relatively well, but the one that uses the same Hessian, which is the less expensive one, is really not doing well. And we took their code and tried to crank down the value of lambda and found that as lambda gets smaller, both approximations are just very, very poor, while cross-validation tends to track the test error well. So this is the regime in which none of these approximations will do that well for at least this very classic logistic regression, L1 regularized logistic regression problem. So I think the key here, in principle, this should work, save for the fact that there is a non-smooth penalty. The L1 regularization is where at least the theoretical assumptions are breaking down and perhaps is what is causing this bad behavior. And so we were hoping to design or address this question of, can we design a robust and computationally efficient approximation of cross-validation for non-smooth problems, given that L1 regularization or nuclear norm regularization, these kind of things are more standard to induce more structure in these models, like sparsity. So putting your optimization hat on, a very kind of natural place to turn is to instead of performing a Newton step, perhaps perform a proximal Newton step. Using a prox function over the non-smooth part of the empirical risk minimization problem. So that's exactly what we proposed. So here, if the approximations from before were simply just minimizing a quadratic approximation to your objective or your empirical risk, we just simply minimize that second order Taylor approximation plus preserving the regularizer. And you can use, again, the leave one out Hessian or the full Hessian for these approximations. Either one, both will give similar-ish guarantees. And so we relied on pretty state-of-the-art solvers to try and kind of scale this to some more practical problems. So we were relying on GLMNet, just out of Stanford, and the Quick, which is for sparse covariance estimation. We were looking at these tools as a way to perform this much faster than the leave one out cross-validation, performing the full thing. And so here's some experiments showing kind of how it performed. So for Quick, we used the same data sets that they had used to show their experiments were faster or were performing state-of-the-art for standard graphical lasso objectives. So what we were showing on the left here is the time it just takes to perform cross-validation versus this just second order Taylor approximation plus a prox turn. So using their software, we were seeing on the order of 20 to 20-ish order speedups across all their experiments. And then we kind of plotted here on the right the relative error, which was below 2% for every experiment. So it seemed to perform just as well as cross-validation, and as well as, which was tracking the test loss quite quickly, but was giving much faster speedups. And then we also, looked at the examples which provided these issues, or provided us or made us aware of these issues. And again, using a prox step over the L1 or the non-smooth regularizer, of course, is going to improve performance, and we saw that empirically. So we were also able to give theoretical guarantees here, and just some highlights. Yeah. Is there a question?
There is a question.
Okay, yeah.
Yes, I unmuted my microphone and you probably heard me
Yeah.
asking. Nicola has a question. Go ahead, Nicola.
Thanks. Yeah, so for the, I'm sorry, it goes back a few slides. For your approximation, you require to have some curvature.
Yeah.
And when we worked on this, where we're struggling was that in the overparameterized regime, you don't have any curvature. And so this approach vastly underestimates the actual cross-validation error. Absolutely. I was wondering if you had any ideas on how to circumvent this issue, other approximations maybe that would make sense.
Yeah, no, that's a really good point. So when D is much larger than N, a lot of these approximations will break down. I was talking to Tamara Broderick about this, and I think she had some ideas, but I'm not quite sure. That actually will be at the end of this part of the talk, kind of the future directions, precisely addressing this regime. So I don't have the solution just yet.
Okay, great, thanks. Neither do we.
I think that is exactly where the frontier of this line of work is. Yeah, so.
Cool, thank you.
We did, yeah, absolutely. What we were able to show is that in the nicer regimes where N is less than D, rather when N and D are of similar order, that you can obtain similar assessment guarantees. Assessment guarantees were similar, but the selection guarantees were actually a bit weaker. And we had examples which showed that this our guarantee, the guarantee of 1 on root in is actually tight. And this is just within the statistical level of the problem. So it's actually quite vacuous. So it seems as though you cannot guarantee that the model selection results you would get via cross-validation will be close to these approximations. So that's another kind of line of open question that we had kind of coming out of this, at least initial body of work, of trying to figure out when can you get similar selection guarantees. So just the contribution so far for this part of the talk is just simply trying to figure out how to get good approximations of the test error more quickly for large scale problems. And as was mentioned by the person who asked the question, like there are a lot of regimes in which this, there are classical problems where this approximations will work well, but there are huge vast array of problems where it will not. And so trying to scale up these techniques to those problems is definitely an avenue of future research. Awesome. So before moving on to the fairness, I'll pause here for any kind of questions.
Yes, we have a question on the chat by Sharan. Would you like to unmute, Sharan?
Sure. So David Duvino and people at Toronto have like this implicit differentiation technique to tune hyperparameters. So it's super fast, but have you like compared against them? Does it work better?
Oh yeah, I've definitely not compared against them. I think in particular because we're maybe working in two regimes. So one thing I would ask is if it works well, are they able to prove that you would get something like the hyperparameters chosen via this technique would be?
Nope. I don't think they have guarantees, but yeah, I mean, yeah.
Yeah, I think we were kind of sticking to the regime where we could prove things would be similar. Hopefully tailored also to practice. Of course, we care about practice. I think that was a huge constraint, so that's just why we constrained what we were comparing to. But I'm really, thank you for making me aware of that work. I'll look into it because I think hyperparameter tuning is clearly an important problem.
Okay, that's fair.
Yeah, no worries. So just in this last part, I started thinking a little through some of the fairness issues, in particular because I did my postdoc in Microsoft Research New England, and there are a lot of people there who are really interested in issues with regard to fairness. And of course, this is becoming a more popular issue in the machine learning. It's becoming more commonplace. So to just kind of provide the context through which we were thinking through some issues in this space. So as I mentioned, this, to me, at least to my mind, fairness is more having to do with kind of the context through which you're embedding or through which you should embed your machine learning pipeline. So how do you formulate your problem? And ultimately, how is this being deployed or applied? And so there are a lot of settings. The way I like to think through it is kind of there's this spectrum where on one hand, you have this large consensus on how problems should be formulated. And so these fairness issues don't tend to arise. And I would say these are like the largest successes of machine learning. And then on the other hand, there's complete disagreement about it. And I think that this is where obviously the fairness issues arise. So one example will be games. Given the structure of games, people agree on the rules, and particularly what constitutes a win or a loss. These tend to be relatively uncontroversial, and I think why you don't see so much more outrage for this quite huge success story with regard to machine learning. It's also straightforward how one could use predictions to aid in decision-making in the context of a game. And then, of course, there are images, given that a lot of visual images are categories to which we all largely agree. There's less controversy. Of course, there's privacy issues and there are some labeling issues, but I would actually put this on the kind of less controversial end of the spectrum for the most part. But of course, there are questions with regards to images as to what extent I am considered a stakeholder. So if it's an image of me, again, my privacy, and it matters what you label me as. So this has its limits. And then medical applications, I would say you're really getting to this side of, maybe there's more disagreements because a lot of medical applications require making decisions in the context of quite big trade-offs. You have a lot of scarce resources. So this is marching to this other end. And then you have kind of this other set of examples where just basic ideas about how these things should be formulated seem natural to us, but aren't necessarily readily agreed upon by a wider body of people. And I think this is where fairness gets thrown in the mix, and yeah, well, characterize these applications. Okay, so I think, coming from a dynamical systems perspective, one thing that was really interesting to me is that when you have these applications where there are people involved, people are dynamic. They respond to decisions that are getting made. And so I think, the fairness community has taken up this issue quite a bit at this point, trying to think through how do you mitigate against changing distribution of data, or a context in which the decisions you make change the distribution of data in ways that you may not like. So in particular for these examples, you have machine learning models allocating resources and opportunities to people, and you also have people responding to how these decisions are being made by maybe trying to game the system or changing their behavior in other ways. And so one work that's pretty kind of mainstream, at least in the economics community, is the following model that was presented by Cote and Laurie in the context of education. So what they described as kind of rule-based way of allocating positions at an educational institution, taking into account or trying to study affirmative action under this kind of setting, is you have an institution, they have people that they've admitted into this institution, and perhaps they have some label that they'll provide to these people as perhaps being skilled and non-skilled. Now, obviously, that's going to be somewhat controversial, probably, to some people. But let's assume we all agree on these labelings. And based on these labelings, they'll decide on an admissions policy. Okay, so I'm going to update my admissions policy. I've let in some people. I've kind of characterize them as good for my institution or not so good for my institution, and I allocate positions to an upcoming applicant pool accordingly. And based on this applicant pool, they have varying features. They get admitted, they have different qualification rates, they present new data. I update my admissions policy and then update my positions accordingly. The thought by Cote and Laurie is that the way these positions get allocated will change the underlying features in the data. And so the model they put forth is, in particular, affirmative action, whether it induces people to actually invest in skills or not. And so they had some way of trying to formalize how exactly their model will kind of affect the underlying feature distribution. This is akin to what's now commonly referred to as performative prediction. So their predictions are influencing the underlying population. And again, this is kind of this cyclical loop. Okay, so what they were trying to answer, and I think that we kind of took this model and tried to elaborate on it, is what are the long-term outcomes of the equilibria that's produced for such a dynamic model where you have the decisions being influenced by the features and the features being influenced by the decisions. And then what decision policies should you have such that the equilibria you obtain are desirable in some sense. So this is kind of thinking through, instead of this one-step fairness thing, this fairness in the long run. And then what kind of interventions produce desirable equilibria? So you have a decision rule, you can think about someone intervening on that decision rule at many levels, and that perhaps could produce desirable equilibria. So right now I'm keeping it quite broad, but I just wanted to kind of provide a high level snapshot of the way this problem is being thought through. So as I mentioned, a lot of people have actually studied this more performative prediction type models. So more recently, a lot of people have thought about a strategic manipulation, which is a setting in which people change their features to game the algorithm. So this is most commonly in like loan settings, and there are a couple other settings as well. Again, we were focused on this kind of educational model where the algorithms reward people appropriately and encourage them to pursue beneficial investments if it does, or reward people accordingly. They have models, and what we also model is that if you have an algorithm that gets things wrong, this could have a discouraging effect from people kind of making beneficial investments. So for example, if you have an algorithm that systematically tends to not admit certain people or have certain admittance patterns, this could be a disincentive for certain groups of people to obtain the desired or requisite qualifications. And so what we really try to add to this model is we had read some empirical economic studies that were talking about the phenomenon where if there are very few people admitted from your geographic region, then you're less likely to apply to certain institutions. So this grouping effect tends to affect behavior in terms of the educational system. So we have people responding to the error rates based on their group, and in particular, their geographical location.
So just a quick note about time.
Yeah.
We will run out of time soon.
Oh,
so
I think I have like 3 slides left. I'm presenting this one.
Okay.
So I think
Okay, that sounds good.
Yeah.
We have time for that, for sure.
Okay, good. So just to be a little bit more precise, although I'm going to keep this pretty high level, the model that was used is that the institution is utility maximizing. So it's choosing qualification parameters based on trying to maximize their true positive rate and paying a penalty for a false positive rate. And then individuals are also utility maximizing. Here, they're going to invest according to this kind of trade-off model where they have some sort of expectation that their investment will pay off based on this true positive, false positive rate on the current model. And there's also perhaps varying costs to investment based on the individual. So certain individuals might be poorer and the cost to investment might be higher. So we kind of employed these 2 models for how institutions might allocate positions and how individuals might respond to these allocations. And then we were just trying to understand what are the equilibria and what happens if we change the objective functions to have fairness criterion. Like, will these equilibria be preserved, or can we induce better ones? And as I mentioned, we added to this true positive rate and false positive rate consideration for the individuals what group membership they had. So they really care about false positive rates and true positive rates with respect to their group. And that was kind of the thing we added to the Cohen-Lowry model. And so essentially, here's what we found. So what ensures good equilibria? Basically, if you have a zero error model, then you can get theoretical guarantees that you are going to achieve a very efficient equilibrium that's good in many respects. In particular, all groups will have the same qualification rate at equilibria, and this will be the optimal qualification rate. So this is a nice result. But as soon as this kind of ability to characterize everybody exactly fails, then fairness can be extremely hard to obtain. Fairness being balance here. And that was something we were interested in, but of course there are other things you might desire to optimize. So here's an example. We have, let's say, 2 groups of people. Suppose there exists a 0-error hiring policy for each group separately, but not together. So I can kind of characterize the blue people separately. I can characterize the red people separately, but there is no, in my class of models, which in this example will be linear classifiers, I can't get both the groups with 0 error. So we can show that in this setting, there will be 2 types of equilibria that'll exist. The stable equilibria will tend to prioritize one group over the other. And then there will be an unstable equilibria in which both groups will have the same qualification rates. So the one that has more balance is unstable, meaning with almost 0 probability you'll converge to this equilibrium. You will have had to start there. So ultimately, what you end up getting in this context under our dynamic model is that it will kind of converge to decision policies that favor one group over the other, because it's not a zero cost. So that's a little bit discouraging from a fairness standpoint, at least under this context. So yeah, that was kind of one kind of conclusion we drew. And just I think this is actually my last slide. So we had some other takeaways as well. I just wanted to make this part brief because it's very much kind of something we're still thinking through. We also looked at interventions that could kind of break this undesirable model or this undesirable trend. But we found that the long-term effectiveness of these interventions really depends on the dynamics, which for the most part are always very unknown. So also not the most positive message going forward. So many interventions that, for example, help in more static settings. So in the setting where you really are just making one decision, you don't have to keep updating it based on how people are responding. So these are, for example, making a classifier for each group, or imposing some sort of fairness criterion. These actually, in a lot of our simulations, and theoretically we were able to prove it in a lot of contexts, end up harming groups. So you really have to have a good understanding of the dynamics in order to show that in the long run, these interventions will be helpful. In this model, we showed that actually there was a really nice intervention that actually helped create desirable equilibria in all cases. It's quite simple, just subsidize the cost of investment for a disadvantaged group. So what we were showing is that basically groups were making decisions based on the cost of investment. So if you just simply subsidize the investment without harming other groups, you actually had more desirable equilibria. But I mean, that's highly dependent on knowing this, on this specific model. Unclear if people are really behaving like that in the real world. So perhaps this model is, perhaps there is some merit to thinking through that intervention. But yeah, I think this is actually an interesting kind of context to study a little bit more, in particular like recommendation systems. There are a lot of settings in which algorithms are impacting human decisions beyond their intended scope, and a lot of it has to do with these changing incentivization structures in which the people are responding to algorithms in certain ways, so filter bubbles and whatnot. So I think this will be interesting going forward. And so yeah, we wanted more of a principled view for how these arise in practice. So this like one outlook thing slide, right? Basically, I think my research at this point is somewhere in the intersection of these 3 bubbles. Yeah, this is actually a little bit more in my job talk, so I was trying to kind of frame myself, but I still think through kind of algorithms in, or rather my research in these kind of three orbits. And so that's where I'm hoping to move forward. So yeah, if there are any questions, thank you for your attention.